Great, thanks. Hi, I'm Noah. I'm co-founder of Emerge Tools, and today I'm going to talk about the search for aliens. So this is Frank Drake, and in 1961, he hosted the first meeting of SETI, which is the search for extraterrestrial intelligence. And attendees of the meeting included many notable scientists, such as Carl Sagan, the astronomer, and Melvin Calvin, who won the Nobel Prize in Chemistry for his work on photosynthesis. And the group was asked this question: how many communicative aliens are in our galaxy, the Milky Way? So to answer it, Drake suggested this equation, which is now known as the Drake equation. This equation multiplies the rate of star formation by a number of factors, such as the fraction of stars with planets, to determine the rate of habitable planet formation. It then multiplies by factors that determine the likelihood of a planet developing life, such as things like having water and atmosphere, and of course I think they all need to have coffee, preferably from Starbucks. The last term in this equation is the length of time the civilizations are active. It's basically the amount of time until they destroy themselves, so let's hope for our sake that this is a very, very long time. And when you multiply all of these terms together, you get the number of planets with communicative aliens. And this has gone on to become one of the most famous equations in physics, right alongside Einstein's E equals mc squared. I even came across it at this interactive exhibit at the MIT Museum in Boston, where visitors could turn these dials on the display to adjust the probabilities and calculate how many planets there would be with alien civilizations. It's important to note that all of this equation is really just an estimate. There's no directly solving for it. But it's rather used as a framework for thinking about the problem and which factors are really important. So we can extend this original equation to the archaeological version, which rather than asking just who we can communicate with, it asks how many aliens have ever been out there in the entire universe, instead of just our galaxy. And in this version of the equation, we don't need that L term that was the lifespan of a civilization. And instead of the rate of star formation, we can consider just the total number of stars in the entire universe. This turns out to be around 10 to the 22nd power. So that's 10 trillion billion, which is an absolutely huge number. And in the full equation, it will dwarf every other term. And what this means is that even if the odds of life developing has a very small chance, the Drake equation will still yield thousands of alien civilizations. So as an example, if the odds of life developing are 1 in a billion billion, so very small number, you still will get around 4,000 alien planets that are out there in the universe. So at this point, you're probably wondering why I'm giving an astronomy talk. Aren't we all software engineers here at a Swift conference? Well, don't worry, I'm not actually going to just talk about astrophysics the whole time. Let's next look at this in software terms. So that archaeological version of the equation is essentially telling us that the odds of life being found is linear in the number of stars. In other words, it's O of n. And in many cases, having an O of n algorithm is going to be a good thing. It might be fast enough for all your applications. But imagine something like scrolling a list of n elements. Maybe these elements are going to be a photo library. Well, how many photos are in your library? I looked at mine, and it was around 45,000, and I'm sure most people are going to actually have a lot more than that. So if you had to perform an O of n algorithm while scrolling a list like this, saying to load new data, you're going to have terrible scroll performance. So an O of n algorithm isn't always good enough for like interactive cases like these, but it is the way that we think about finding aliens. So now hopefully you followed along with the argument that the Drake equation used to estimate aliens is similar to an O of n algorithm, but you're probably wondering, why do you care? You probably aren't using time complexity in your work as a Swift developer very often. Well, I think that the real takeaway from this equation is to look for scale factors. And what that means is just like the number of stars provided this big scale factor for determining the likelihood of aliens, you can look for similar scale factors in your own work. And you can use that to amplify your work to a broader audience and have a greater impact. So you might have scale factors in your own work like the number of downloads of your app, or the number of users, or even something like the number of lines of code in your code base. And many important metrics are going to mimic the Drake equation. It's just going to be a few multiplying factors. And some of these factors will be big. So let's look at an example. The carbon footprint of an app is one of my favorite examples of this, and it has many factors. One piece of it is the energy it takes for you to download the app itself before it even gets used, just to get that app on the phone. And that's composed of energy used from data centers through the routers of the internet, all the way to the energy used by the phone itself while it's performing the download. And we can estimate the amount of carbon used for an app install based on the efficiency of the power grid per megabyte transferred. In this example, we'll use the US power grid efficiency. So we can take a typical app download size, say 110 megabytes, and then when we multiply these factors together, just like we do in the Drake equation, you get the total carbon footprint of one app install. So the equation that we use for this has two variables. It's the download size and the number of downloads, which then get multiplied by the power grid efficiency. So for one download, it's not very much. This is going to be a small number. But let's extend this. First, note that it's not just app installs, it's also app updates. And while an update size is going to be slightly smaller, thanks to only the modified files being included in an app update package, the total number of updates is actually going to be a lot larger than the number of downloads. So we can create a new equation that includes both these terms, the update and download size, as well as the number of updates and downloads. So these are all multiplied together by the carbon efficiency to give a more complete picture of the carbon footprint of your app installs. And these are just some factors that there are some factors that can be very large. In fact, Spotify wrote a blog post about this where they stated that over 20 billion updates were installed on their apps in 2022. So this is just like the number of stars in the Drake equation, where a small change now in your app size can be scaled by this huge number of installs, resulting in a big change to your carbon footprint. And in fact, just a 1 megabyte change in this case can be as much as 5 round-trip flights from Los Angeles to London. So if you're working on an app like this, it means that you can have a very big impact just from working on something as seemingly small as app size. Now, I should also note that just because we saw that there's a big scale factor associated with app size doesn't necessarily mean it's the most important thing. There are a lot of other aspects to a phone's carbon footprint. One of those is the embodied carbon, which is how much it takes to build the phone itself. And that's still going to be higher than the operational carbon, which is what it takes to actually power and use the phone through its lifetime. So this suggests other factors like improving performance and support for old OS versions so that users don't have to buy new phones as often is also going to be something that's very impactful. But of course, another reason that people are buying new phones is when they run out of storage. So you could always make the argument that app size matters there as well. So another example of the Drake equation principle in practice is from this WWDC talk a few years ago on app launch time. And in this talk, Apple says that for every millisecond they shave off an app's launch time, a total of 162 days of time is saved, which is how long it takes for a rocket to reach Mars. So this means that apps are opened many billions of times a day, which is going to be another really huge scale factor. We can make our Drake equation analogy for this similar to the carbon footprint equation. It's just the amount of time you reduce from app launch time multiplied by the number of launches in a day. And this is how we can show that to get to 162 days saved, you need around 10 billion launches. Of course, only Apple can take advantage of this large of an app launch scale factor because their OS code is going to affect the launch time of every app. And if you improve your own app's launch time, it's going to be scaled by a smaller factor because presumably people are using more than just your app. But it turns out there are other very large scale factors we can consider just related to your app's launch. So let's consider the number of lines of code in your app as a scale factor. This can be really large. In fact, Uber has stated that they have a couple million of lines of code in their app, and typically this number is only ever going to be growing. So I think it presents a lot of potential. For example, if you could make every line of code just 1,000th of a millisecond faster, your app would get 1 second faster. And that's, even though it's a small improvement per line, it's overall a huge improvement that users would definitely notice. So let's make this a bit more concrete by looking at how an instruction is executed in the CPU. So when a CPU core needs to run an instruction, first it has to get that instruction. And the phone's RAM could hold the data, or it could only be in the file system as part of your whole app binary. This tiered memory has big differences in size. with storage going up to a terabyte, RAM being around 8 gigabytes, and CPU being measured in the megabytes. So as the size increases, the latency also increases by an order of magnitude between these tiers. When the CPU fetches an instruction, it's fastest if it can be found in the cache, slower if the instruction is in RAM, and if it needs to go all the way to the file system to find the instruction, that's the slowest it gets. But once it finds it there, it gets copied into RAM and then brought into the CPU. So with many instructions, the time it takes to execute these instructions or lines of code can really add up, especially when it's being read all the way from storage. So it turns out there is a way to improve this, and that's with order files. They're a way to leverage this scale factor of the number of lines of code in an app to improve these CPU instruction fetches. It does it by co-locating instructions that are frequently accessed, which allows them to be loaded in a batch and avoids the multiple round trips into storage. This only works well with sufficiently large code bases because there needs to be enough of these instructions that it actually makes a difference for loading them in a batch, and this really small performance benefit adds up because it gets multiplied by this scale factor of your lines of code. And my company, Emerge Tools, has a service that generates these, and for some large apps, we've seen as much as an 18% improvement to app launch time just from this really small change per line. So what we've seen so far was all linear scaling, which is O of n, but you can also have sublinear scaling. That's things like O of log n, and that doesn't grow as fast when n increases. Usually this is very good because it'll make your algorithm even faster. But less fun is when you have something like super linear scaling, like O of n squared. This grows much faster and can quickly cause problems. To visualize it, you can see the solid blue line is going to be your linear scaling, and the quadratic line above it grows a lot faster off the edge of the graph. So one example of this in Swift is going to be protocol conformance checks. A conformance check happens when you use the as keyword to check if a type conforms to a protocol. It's not really obvious that this is happening in Swift, but this is actually a runtime operation. So it's kind of like a function call, not a compile time operation like you might be used to from other languages. And the way this function call works is a record of every conformance is stored in the binary as a list of pairs like this, with each containing the type and the protocol. So when the cast operation is evaluated, this list is iterated. So it's linear, O of n squared. O of n. So each conformance check is linear in the number of conformances that your app has. And it's important to note that this isn't just the times that you directly use a protocol in your code. It includes all conformances in your dependencies, like first-party dependencies from Apple and any packages you use, anything like that. And many apps will have greater than 100,000 of these conformances. It's easy to make them add up. For example, when you use something like Codable, you're really using two protocols, encodable and decodable. And it's also common to code gen Swift code that uses protocols, and these can grow really fast. So it's a big scale factor, and we can ask ourselves, is linear too slow for something like this to be in your app when you have 100,000 of these? Well, that's a trick question, and the title of the slide should give it away, that it's even worse than linear, it's actually super linear. So a single protocol conformance check, like we showed, is linear. It iterates that list of conformances in the binary. But when your app is used, really every conformance is eventually going to be checked unless you have dead code in your app with some conformances that aren't being used at all. So here's some pseudocode that sort of explains what's happening. There's this outer loop that is being executed throughout the user using your app. So this code isn't directly in your app, but it's what happens as someone is going through your entire app. Eventually, they'll use every conformance, and for each one, there's this inner loop that is hidden by the protocol conformance checks. Even though it's just that one line that is in a loop, internally, that's a function call that's going to be doing a linear check. So overall, the nested loop is going to be n squared. So these large scale factors can present a big performance problem. Even when scaling linearly, like in the Drake equation, might work, this quadratic scaling definitely won't work. And that's when issues are going to appear. To mitigate this in your code base, I have just a couple quick tips. One is to just avoid having too many conformances. Things like Codable can maybe switch to just using decodable. And to reduce the number of dynamic casts that you are performing in your app, because it can happen a lot more often than you might think. Like when you get a string representation of an object, internally that will do multiple checks to see which protocol the type conforms to, how to turn it into a string. I go into a lot more detail in this in my blog posts and previous talks if you want to learn more about this specific topic or how to improve it in your app. So as we've seen, sometimes you can use scale factors to improve things like the time it takes to launch your app with order files, but you're not always scaling something good. So another example is we can think about the number of bugs in a code base. So with a show of hands, who thinks they can write 10 lines of code without introducing a bug? Hopefully some people can write 10 lines of code. All right, we've got a few. But like 100 lines, probably going to be a lot harder, right? And if anyone can write 1,000 lines, you come talk to me afterwards because maybe we have some job openings. But some ideas for how often bugs appear in practice has been reported, like Microsoft says that there are 10 to 20 bugs per 1,000 lines of code, and that they have half a bug, whatever half a bug is, in their release code. And overall, the industry average seems to be about 1 to 25 bugs per 1,000 lines of code. So if you have millions of lines of code, which like we saw earlier, some apps have, odds are you're going to have thousands of bugs. And this is an example of a scale factor really unavoidably scaling something that you don't want to be scaling. So, and that brings me to really the main point, which is to write less code. I think it's the most important change you can make to an app is just reducing the number of lines of code. And the principles we looked at today, this Drake equation, shows us how helpful reducing the number of lines of code can be. I think it's similar to this general design principle that good design is as little design as possible. We can sort of make the programmer version of that, of good code is as little code as possible. And it's actually the primary motivation behind a lot of what Emerge Tools creates. Like size analysis is something that we make that is meant to reduce app size, often by removing code. And Reaper, which identifies dead code in an app through production measurements so that you can remove it. It's so key, I have a second slide on this point. And last month, there was an issue of iOS Dev Weekly, which I imagine a lot of people here would be reading, where Dave talked about the consequences of including Swift packages in your app. And he mentioned that all software is buggy. And this was a reason to have, to avoid having unremovable dependencies adding code into your app. And I really couldn't agree more. This is why I often suggest that using something like CodeGen is not the solution, because it just adds more code, which is always going to be buggy. And as we saw with our equation for estimating the number of bugs, you can get an idea of how quickly these bugs can add up. And it's often easy to use more code as a quick way to solve a problem, such as adding a package, but it often ends up hurting more than it helps. One example of this is snapshot testing. At Emerge, we do snapshot testing with no code. We simply generate snapshots from the existing Xcode preview in a code base. So it avoids having to write a test manually or to code gen anything, which is common practice in other snapshot generation techniques. So when I think about writing less code, I think about it as one of these fundamental principles of app development, kind of in the same way that many other engineers would look at the laws of physics to determine what it is or isn't possible to make. We can look to some fundamental laws like these also to understand our app. And we have a higher law than the laws of physics, of course. It's the App Store guidelines that will often prevent us from doing what we'd want, even if the laws of physics would otherwise allow it. But lessons from the Drake equation, they give us this other unavoidable lesson, which is that less code is better. It means you'll have less bugs. So one last idea on the topic of lines of code is what if you write tests that have coverage of the many lines of code that you have in your app? Is more test coverage going to be better? Well, I think this conflicts a bit with our fundamental principle, because writing more tests, it might mean writing more code, and that code will unavoidably have bugs. So don't worry, I have the solution. We just not write tests. Then, of course, they won't fail and everything will be fine, right? Well, yeah, I'm not actually going to advocate for you to not write any tests at all. Just to think about these general principles and recognize that there's eventually going to be a diminishing return where writing more code at a large scale would actually cause problems. There are other solutions, though, to increase your test coverage. You don't actually need to write a test to get high test coverage. You can do something like tracking the code used in pre-release versions, which might go through manual QA testing or beta users. And anything that doesn't have coverage in these versions can hopefully be deleted. This is something that my company works on with Reaper, where we can track code used in pre-production to give you an idea of the coverage of your beta testing. You can also extend this idea through snapshot testing to get automatic tests for declarative UI that it's easy to make an Xcode preview for. And that could get a much higher percentage of your code base having code coverage without actually having to write a separate test. So now that we've looked at a lot of different scale factors, I want to briefly mention ways that you can find your own scale factors to have the biggest impact. One is that you can look at what's used the most. For example, if you make a change to the build system that's actually building the code in your app, you can affect all the code in your app. That's kind of like what we did with order files, where we affected every line of code to make it faster. And if you work on a framework, you can scale your impact to many apps, not just the apps that your company makes or the framework on its own, because hopefully many people will be using your framework. You can even start a company. That's what I did to scale the impact from the single app I was working on at Airbnb to now all the apps that use my software. Or start or attend a conference like this. And also speaking at a conference like this hopefully helps multiply your ideas by everyone in the audience, like I was hopefully able to do today. So to wrap up, if you take away one thing from this talk, it's to think about looking for aliens the next time you plan a project. And what this means is to look for scale factors and be careful not to introduce new scale factors that you don't want, but also to leverage the ones that you already have. And if you want to talk more about this, come find me after the talk, or you can get in touch at SonNewton3 on many of the usual social networks, or you can scan the QR code. And I wanted to give a shout out to Ken for helping to spark this idea about the Drake equation, and to my team at Emerge. Some of them are right here in the front row. You can find them around the conference for the rest of the week. Thank you.